Let us next start exercises 5.2. In these first two exercises, in each one of them a complex number will be given and we have to find its modulus and its arguments. And the first one is -1 minus root 3i. So finding the modulus is a simple matter because the formula for modulus, the definition for modulus is this: square root of real part square plus imaginary part square. In this complex number, -1 is the real part and minus root 3 is the imaginary part. Again, I am repeating something. Do not make the mistake of thinking that minus root 3i is the imaginary part. The imaginary part by definition is the real number itself. Okay, it does not have I. So only minus root 3. So if you do the calculation, you find 2. So that is the modulus or absolute value of our z. Next, we also know that a single complex number has infinitely many arguments. Say our complex number has theta as an argument. It is one of the infinitely many arguments. Then the relationship between theta, r, x and y, that is real and imaginary parts, those relations are these. The real part, which is -1, equals r cos theta. R here is 2, so 2 cos theta. And the imaginary part equals r sin theta. So we get these two equations: cos theta equals -1 divided by 2 and sin theta equals minus root 3 divided by 2. Now we have to find a value of theta. And this is where our knowledge of solving trigonometric equations will become useful. So let's see how. So going back to our solutions to trigonometric equations, we first note this: cos theta and sin theta are both negative. This means that our angle should lie in the third quadrant. Why? Because sin theta and cos theta, if you remember, are respectively the y coordinate and x coordinate of any point on the unit circle centered at the origin. And in the third quadrant only, both these coordinates are negative. We note one more thing, that cos 60 degrees or cos pi over 3 radian equals 1 divided by 2. This is something we know, and this does not involve this minus sign. So we know that somehow the angle 60 degree or pi over 3 radian should be involved in this calculation. But pi over 3 radian lies in the first quadrant, only. We want our angle in the third quadrant. So we guess that if we add pi to pi over 3, then this angle may be a candidate of our theta. And then we verify if that is really the case. Let's calculate cos pi plus pi over 3. Cos pi over 3 minus sin pi over 3. Because sin pi is 0, this second term vanishes. Cos pi is -1 and cos pi over 3 is 1 divided by 2. So we really get -1 over 2. What happens when we calculate sin pi plus pi over 3? Similarly, sin pi cos pi over 3 plus cos pi sin pi over 3. Because sin pi is 0, this term vanishes and here you get -1 and this one is sin 60 degree or sin pi over 3 radian is root 3 divided by 2. So you are getting this one also. So yes, this is one value of theta, which is pi plus pi over 3. Okay, so that was only the rough work. How should you write the solution in this part? You just straight away write the angle. Since cos of 4 pi over 3 is pi plus pi over 3 is -1 over 2 and sin 4 pi over 3 is minus root 3 over 2. So theta equal to 4 pi over 3 is an argument of z. If you want to make it a bit longer, then you can show that calculation. Say you actually calculate cos 4 pi over 3 by applying the addition formula for cosine. Okay, so that way you can write something here if you really want to show the calculation. Oh, and one more thing, please show the rough work alongside the solution. You draw a vertical line and on this side of the line you do your rough work. Show that, don't just simply do it elsewhere and then you straight away write this angle. Don't do that. Okay, show the rough work. So this way we get one value of argument, but what about the other infinitely many values? That's just easy. You add any integer multiple of 2 pi, so that way you get all the other arguments where n is any integer. This is where the solution ends, but there is a note. You may remember that we defined arg of z to be any argument of z. Truly speaking, that is actually the set of all arguments. Here we are not talking about principal argument. We are talking about all the arguments at once. So in that sense, you can write argz as the set of all arguments. Although I would advise you to not do that. If you are writing an exam, don't do this. You just write in words as a sentence, hence all the arguments of z are this, where n is an integer. Okay, so that's it. For this second one, the complex number is minus root 3 plus I. So modulus, like before, turns out to be 2. And again same procedure, let theta be an argument of z, and this time we are getting these two equations. The real part equals modulus cos theta and the imaginary part, which is 1, equals modulus sin theta. So those equations turn into these. Cos theta equals minus root 3 divided by 2 and sin theta equals 1 divided by 2. So now cos theta is negative and sin theta is positive. So we are in the second quadrant. That is, our theta should be in the second quadrant. And at the same time, again, we just take the numerical value and guess 1 theta, which won't really be our theta, but it will be involved in the calculation. Cos 30 degree or cos pi over 6 radian equals root 3 divided by 2. But we want an angle in the second quadrant. So we subtract this from the full pi. Okay, so that way we get an angle in the second quadrant as this angle, 5 pi divided by 6. And then you have to check if this really is the angle that will give you these values. That part is left to you. It really is the angle. Okay, so you show really that cos of 5 pi over 6 is this value and sin of 5 pi over 6 is this value. That you will have to do it. So we just proceed to write the solution and complete it. Okay, so that is the solution. Because cos 5 pi over 6 is minus root 3 over 2 and sin 5 pi over 6 is 1 over 2. So 5 pi over 6 is one value of theta. It is one argument. So all the arguments are obtained by adding integer multiples of 2 pi to that. And that's it. These are all the arguments. And the modulus is 2. In number 3, and actually in the remaining exercises, the given complex numbers have to be expressed in the polar form. So in the third one, the complex number is 1 minus I. The procedure is same. And in this case, you don't even have to find all the arguments. Just one argument is enough for you to write the complex number in polar form. So if we you can first give the complex number a name. So we call it z. Z is 1 minus I. Then same procedure, you first find the modulus, which in this case is square root of 2, and let theta be an argument of z. So from that you get these two equations. The real part, which is 1, equals modulus times cos theta, and the imaginary part is minus 1, which is root 2 sin theta. And that gives us these two equations. Cos theta equals 1 over root 2 and sin theta equals minus 1 over root 2. And then you can go through the rough work also. In this case, cos theta is positive but sin theta is negative. So the angle should lie in the fourth quadrant. Now it's not always necessary to go anti-clockwise like that. You can go clockwise as well. It's up to you. Whatever you find convenient, you should do that. So in this case, just a moment of reflection tells us that this angle works minus pi over 4. We do not even have to add or subtract any pi or 2 pi to this guessed angle pi over 4, which should be involved in this calculation, because cos pi over 4 is 1 over root 2. And it works because cos minus theta equals cos theta. So even if you take a minus sign here, you would still get 1 over root 2, which is what we want. And sine of minus theta is minus sine theta. So that way this becomes minus 1 over root 2. And when you multiply these things by root 2, you get back 1 minus I. But in this form, we have the polar, this is the polar form of the given complex number. Because it is going to be exactly same for the other subsequent exercises, so I will just give you the answers to these next ones. So you go through the entire work, which is nothing really that difficult. So these are the remaining ones. The fourth one is minus 1 plus I. It turns out that you can almost instantly see what its modulus is. It will be square root of 2, because square root of minus 1 square plus 1 square. And argument like that, using that procedure, you can find one argument easily, which is 3 pi divided by 4. Note that the complex number lies in which quadrant? The real part is negative and the imaginary part is positive. So in the second quadrant. So from that you can guess what your angle should be. This one is minus 1 minus I. Here the complex number lies in the third quadrant, because both the real and imaginary parts are negative. So that way this is the polar form. And again I am saying, I am repeating something from our previous discussions. Perhaps I should not say the polar form, because this theta can change. So it is one polar form. Okay, but usually we say the polar form. This sixth one is very interesting, minus 3. Minus 3 lies on the negative x-axis or negative real axis. For that type of points, you already have a fixed value of theta, which is pi. So 3 times cos pi, and what is its modulus? Modulus is absolute value, because this is real number, so just the minus sign, it's not there. So you remove the minus sign, you get the modulus. Cos pi plus I sin pi, and you can instantly see here that that is really the case, because sin pi is 0 and cos pi is minus 1. And then you again have this another one, square root of 3 plus I. In this case the modulus is 2, and the one of the arguments turns out to be your ordinary pi over 6. It lies in the first quadrant though. And this final one is again something like this. This is purely real, this is purely imaginary. It lies on the imaginary axis. And for them, pi over 2 is one argument, 90 degree. Oh, and one more thing, the modulus is 1 here. However, you may have the tendency of not writing 1 here. Please do write, because ideally the polar form should show both the modulus as well as arguments, whichever argument you choose. So you write 1 here and then you write that pi over 2 as your argument. So this is the polar form of I. So with that, this set of exercises ends. After that, there is one more section in this chapter which involves solutions of quadratic equations which do not have real roots. So it is that case where the discriminant of the quadratic equation is negative. But by now you know where all these things are going, that their solutions will be complex numbers. So there are some equations, so we will solve them and complex numbers will be over. So that's just it for tonight. So see you tomorrow with a new upload. Until then, this is me, Lucifer from a mathematical room. Have a nice day.